Here is a problem on FIR filter design using windowing technique. This is a commonly asked question in the university examination. Here the desired frequency response is given. You have to design using the Hanning window and you have to determine the H of Z also given n equal to 9. This type of filters we can design in two methods, either using the causal sequence or using the non-causal sequence. So we are following the causal sequence method. So before solving, let us look into the difference between the two. The two methods are given in the Nagurkani's textbook, page number 6.57. So very similar problem is given here. So this is using the causal sequence. For a causal sequence, h of n equal to h of n minus 1 minus n. In such cases, you have to choose the frequency response as e raised to minus j omega alpha, where alpha is given by n minus capital N minus 1 by 2. Then as usual, we can determine the desired impulse response by taking the inverse Fourier transform and so on. The second method, using the non-causal sequence. Non-causal means we will be having impulse response in the negative x-axis, that is h of minus n equal to h of n. So in this case, after the designing, you have to shift the sequence to the right of the x-axis in order to make it as a realizable one. So in both cases, the final answer will be the same. So we can follow the non-causal sequence system. The desired frequency response of the FIR filter is given by the specifications shown here. So let us choose symmetric impulse response with the symmetric condition h of n equal to h of n minus 1 minus n. So this corresponds to the causal system. The ideal frequency response HD of e raised to j omega for low pass FIR filter is given by HD of e raised to j omega equal to e raised to minus j alpha omega for omega between minus pi by 3 and plus pi by 3, where alpha is given by n minus 1 by 2. In our case, capital N equal to 9, so 9 minus 1 by 2 equal to 4. So we can write n equal to 9. So the desired impulse response HD of n is given by the inverse Fourier transform of the HD of e raised to j omega, which is given by HD of n equal to before that, let us write the expression also. HD of n equal to 1 by 2 pi integral minus pi to pi HD of e raised to j omega to e raised to j omega and d omega. Now substituting, we get HD of n equal to this expression. Simplifying, we get e raised to j omega into n minus 4 into d omega. Computing, we get expression in this form. Substituting for omega equal to pi by 3 we get an expression like this. Here we can see e raised to, this is in the form of e raised to j theta minus e raised to minus j theta divided by 2j. It is equal to sine theta. So we can replace this part with the sine term. Simplifying, we get hd of n equal to sine pi by 3 n minus 1 divided by pi into n minus 4. In this case, when n equal to 4, it will be a division by 0, means it will become an indeterminate. In such cases, we have to apply the L'Hospital's rule. So first of all, we can determine hd of 0. So this is obtained by differentiating numerator and denominator with respect to n. So we get, this is hd of 4. When n equal to 4, the denominator will become 0. Now after differentiation, we get the expression in this form. So when n equal to 4, this will become cos 0 equal to 1. So that we get pi by 3 by pi, which is equal to 1 by 3. So hd of 4 equal to 1 by 3. Now hd of 0 equal to hd of 7 minus 1 minus 0. Sorry, 9 minus 1 minus 0, which is equal to hd of 8. Substituting for 0. hd of 0 will be obtained as 0.0689. It is sine minus pi, so it is equal to 0. Next, hd of 2, which is equal to hd of 6, which is equal to sine pi by 3 into 2 divided by minus 4 pi, which is equal to minus 2, is equal to 0.1378. Then hd of 3 equal to hd of 5, which is equal to sine pi by 3 to minus 1 divided by minus 4 pi, which is equal to 0.2757. And hd of 4 we have already computed as 1 by 3. So we get the desired impulse response sequence as this one. 0.0669 corresponds to n equal to 0, then n equal to 2, which is 0, then n equal to 3 to 4, then you have the symmetric values in the other side. Next, we have to multiply the filter coefficients with the Hanning window. So for the Hanning window, the causal sequence is given by the lower equation, that is 0.5 minus 0.5 cos. The upper equation is for the non-causal sequence. So we can take this one. Here the Hanning window is given by this expression. Now we can determine the window sequences. First, h of 0, which is equal to wh of 8, which is equal to, here we can see when n equal to 0, this cos 0 become 1, and this will be 0.5 minus 0.5, it will be 0 itself. N equal to 1, value is 0.1464. Next, wh of 2 equal to wh of 6. wh of 2 equal to 0.5, then wh of 3 equal to
W Hanning of 5 equal to 0.8536 equal to 1. WH of 4 equal to 1. The Hanning window sequence corresponding to n equal to 9 will be obtaining like this. The Hanning window sequence and the desired filter coefficients have calculated. Now the impulse response can be obtained by the 1 by 1 multiplication of HD of n and WH of n. After 1 to 1 multiplication, we get the H of n as shown here. Now, once we have H of n, this H of Z system function can be determined using the expression H of n is raised to minus n. Now, 0 into z raised to 0 plus 0 into z raised to minus 1, then 0.0689 into z raised to minus 2 plus 0.2353 z raised to minus 3, etc. Now these can be combined. The coefficients are common here. In such cases, we can combine the terms and z raised to minus 2 plus z raised to minus 6, and finally we get h of z as shown here. Now suppose it is asked to determine the frequency response, then replace z with the e raised to j omega. Replace each z with the e raised to j omega, we get the frequency response. So that is the final answer. Thank you.